Now, here we go. Well, last time we were talking about the Michael reaction, just introducing it, and the Michael reaction is an example of a conjugate addition reaction. You've seen those before in chapter 13 when you had a cuprate add to the beta carbon of an alpha-beta unsaturated carbonyl compound. Only difference now is that in the Michael reaction, the nucleophile is not a cuprate but is an enolate. Though most organic chemists use the term Michael reaction more broadly to refer to conjugate addition no matter what the nucleophile is. So today we'll be talking about a nucleophile, meaning the enolate, attacking the beta carbon of an alpha-beta unsaturated carbonyl compound as an electrophile. That's going to be the pattern. Enolate nucleophile, alpha-beta unsaturated carbonyl compound, electrophile. Now, before we dive in, I want to anticipate some questions and confusion that happens not only with the Michael reaction, but with the second thing that I'm going to talk about today, which is the Robinson annulation. And that is, some of you are starting to realize that it can be difficult to know what product you're supposed to predict. For example, the classic aldol reaction of acetone leads to one of the aldol products, which is itself an alpha-beta unsaturated carbonyl compound. Well, I just now told you we're going to learn that such things are indeed electrophiles and are reactive at the beta carbon. So what if now an enolate from your starting material attacks the carbonyl carbon in a Michael reaction? I will lead you through that in more detail later, but I'll just draw for you what the product would look like. Oh, how about that? And then, though you're not thinking of it at this point, this molecule itself has alpha protons and carbonyl carbons spaced such that if we did an intramolecular aldol reaction, we could close up a six-membered ring. And do a subsequent elimination reaction. That's the product of that. Now, by the end of today's lecture, you're going to be familiar with the Michael step and a subsequent intramolecular aldol. That's the Robinson annulation. What's going to trouble you is that now and ever after, you are going to be unsure when I start here what you're supposed to draw. Are you supposed to draw just the simple aldol product? Are you supposed to go on to do the Michael product? Are you supposed to go on to do what we will call as the Robinson annulation product? The answer is all of these are in equilibrium with each other, and the outcome is context dependent, and the text doesn't delve into how you're supposed to know whether or not to get to one or the other. Instead, synthetic chemists use these possibilities to design experiments, design approaches, and then they go try them and tweak them until they work. So for you, you have to trust that I'm not going to give you this starting material and then say, this is option A, this is option B, this is option C, guess what I'm thinking, right? I won't do that. Instead, the way the text tends to ask the question is, it will say, which of these is the Michael addition product? Or which of these is the aldol product? Or which of these is the Robinson annulation product? In a mechanism question, it's less open-ended. You'll have starting material and product, and you'll have to push arrows to get from one to the other, but you'll know where you start, you'll know where you end. The other way your text will approach this problem is say, here's two starting materials, react them together in the Michael reaction. So you have to know what the Michael reaction is, and then you'll have direction. Or, excuse me, use these two starting materials, react them together via the Robinson annulation. You'll have to know what that is. Alternatively, sorry, I'm not getting emotional here. My voice is just tired. You don't believe me, yeah. It's just get so emotional when we talk about chemistry. Alternatively, they can give you a Michael reaction product and say what starting materials lead to this product via the Michael reaction, or what starting materials lead to this product via the Robinson annulation. Okay. So with that in mind, let's dive back into a specific example of the Michael reaction. In the Michael reaction, you're going to have a nucleophile, which is going to be an enolate. Of course, when it's shown you, it won't be in its enolate form. You'll have to make the enolate with a base. And then your electrophile is going to be the alpha-beta unsaturated carbonyl compound, which is electrophilic at the beta carbon. So here's an example from your text. Here's the alpha-beta unsaturated carbonyl compound. We're working on suppressing the panic reflex on seeing rings of any kind, so we're just throwing some in there randomly. There you go. And then the enolate, in this case, is going to be this one where the alpha proton is adjacent to 2 carbonyls. It doesn't have to be that way for the Michael reaction. It is often that way. You will often use as a starting material something where you can make an especially stable enolate. As you know, the pKa for that proton that's alpha to 2 carbonyls is quite low. You don't have to have it memorized. I just know it because I've taught the class a couple of times. So here is the enolate, and here is the alpha carbon on the enolate that's going to be doing the attacking. Sorry, that's not the enolate. You've got to remove the proton first. In this case, we would use a base, ethoxide, which can completely and 100% yield remove that alpha proton because it's especially acidic. Then this is our nucleophile. Alpha carbon of our nucleophile. Now here's our electrophile. Here's the carbonyl carbon, alpha carbon, and beta carbon. Enolates prefer to attack alpha-beta unsaturated carbonyl compounds on the beta carbon because that's where most of the LUMO is. If we stopped there, we'd have too many bonds to carbon, so we have to move the electrons out from the pi bond onto the alpha carbon. That makes sense because if the electrons are on the orange alpha carbon, they would be stabilized by resonance. So I'll put the lone pair that used to be the pi bond on the alpha carbon. Here in red is the new pi bond that we made, and what's on the other side of that is the purple alpha carbon from my enolate. In other words, this enolate is this portion of the molecule, and this electrophile is this portion of the molecule. And the new bond is formed between the beta carbon of the alpha-beta unsaturated carbonyl compound and the alpha carbon of the enolate. And then in the final step, we pick up a proton from the conjugate acid of our base, which in this case is ethanol, and that gives us the Michael product. Couple of things to be aware of, some structural features to use to recognize a Michael product. I'll just highlight the portions that come from the enolate and in purple and the original alpha-beta unsaturated carbonyl compound in orange. Notice that the bond that we formed via the Michael reaction is the bond between the beta carbon of the alpha-beta unsaturated carbonyl compound and the alpha carbon of the enolate. Notice that that purple alpha carbon is gamma to the orange carbonyl. Notice that the 2 carbonyls are delta to each other, or are 1, 2, 3, 4, 5 atoms away. In fact, one of the key ways that you can recognize the product of a Michael reaction, that you can recognize a Michael product is, it is a 1,5 dicarbonyl compound. Okay, questions about that? Yeah.
So it's always reliably a 1,5 carbonyl.
Yep, Michael product is always reliably 1,5 dicarbonyl. Good. Yeah.
And then we could take this one step further by adding H3O plus.
Sure, if you wanted to, you're recognizing that this is a beta keto ester, which is sort of from the malonic ester and acetoacetic ester synthesis, you know that you could hydrolyze that and decarboxylate if you wanted to. Yep. Not necessarily part of the Michael reaction, but if you were trying to make something else, you could. All right. Yes?
What was the Robinson reaction?
The Robinson one, we're not there yet. We'll get there. It follows the Michael reaction, but yeah. Yep, stay tuned. After a few messages from our sponsors. Okay, what else? Okay, let's do one in the predict the product sense together, and let's do one in the thinking backwards sense together. So this example comes right out of your text, and the text says what product is formed when each of the compounds is treated with sodium ethoxide in ethanol. They don't tell you that it's the Michael reaction, but there are clues, context clues present that would indicate what you are meant to do. First, remember that in the Michael reaction, the electrophile is an alpha-beta unsaturated carbonyl compound. So, if one of your starting materials is the alpha-beta unsaturated carbonyl compound, that's a good indicator that this is perhaps a Michael reaction. And indeed, we have one of those. Here is the alpha carbon, here is the beta carbon, there's the pi bond between the two. So it's a pretty good guess that this is going to be our Michael electrophile. Another way of saying a Michael electrophile, sometimes chemists will use the term acceptor. It's the Michael acceptor. The beta carbon is going to accept the enolate. That means the other partner must be the Michael nucleophile, which means we're going to need to make an enolate. Now, I chose this example deliberately because some of you are going to look at that and freeze up because you're not sure what to do with the CN. My goal is to help you figure out how to work things out based on what you know, even when you see something unfamiliar. So one thing that will help if you see CN is to actually draw out its Lewis structure, which is a pi bond between two pi bonds and a sigma bond between carbon and nitrogen with a lone pair on the nitrogen. Another thing that will help is to compare this with this beta diketone. Do you see any similarities between the two? Still nothing. Okay, that's fine. You've got, let's remember that when you have an alpha carbon when you have a proton that's alpha to two carbonyls, the resulting enolate, if you remove the proton, is resonance stabilized in multiple places because the negative charge on the alpha carbon can be delocalized onto not only one oxygen but the other. That makes sense? You've seen that before? Okay. Let's make the enolate from this alpha carbon and see if there's anything similar going on. We're using sodium ethoxide in ethanol, so this is our base. Sorry, here is the enolate. Now, most of you are going to see pretty clearly that this lone pair can be delocalized on that oxygen, and that's good. Turns out I can also draw the lone pair is on the alpha carbon is also conjugated with the CN group, such that I can make a pi bond between purple alpha carbon and the nitrile carbon, and then I would just break one of the pi bonds between carbon and the nitrogen, and that will generate this resonance structure. Not a separate molecule, but a resonance structure of the same molecule in which now the nitrogen has a negative charge. So what you learn from this is that an adjacent CN group is like an adjacent carbonyl. It can make an alpha proton especially acidic too, because the CN group is an acceptor of electrons via resonance. All right, so that helps you say that, okay, I need to make the enolate for this compound. I'm going to draw that enolate one more time just to avoid all of the colorful shading so we can predict what the product is. We'll shade the alpha beta unsaturated carbonyl compound in orange. We'll shade the nucleophile in purple. So just predicting the Michael product, I encourage you to go through the mechanism on your own. We won't do that now because you've already seen it. But to draw the Michael product, I need to draw the alpha carbon and the beta carbon, and then I need a new bond between the beta carbon of my electrophile and the purple alpha carbon of my nucleophile. So this here is going to be the purple alpha carbon. That alpha carbon is attached to a CN group and a ketone. And I'm done. That is the product of the Michael reaction between those two starting materials. That was lovely applause. Yay. Yes?
So initially in this, to pull off our first hydrogen, we used OET.
Yeah.
And previously we used that so that it would like conveniently mix up if things happen to go wrong and like just replace it.
Right.
In this situation, would you consider using just oxygen methyl or whatever?
Yeah, you could use any base to do this. This is just what the problem suggested.
Or just like CN minus?
You would not use CN minus as a base because it's actually not a really good base. But you could use OH minus or ETO minus, yeah. None of our starting materials is an ester, so you don't have to worry about potential reactions with the ester. Up here, you sort of did because that ester was there. Yeah?
What's the pKa of the hydrogen on the CN?
The pK for the hydrogen adjacent to the CN, I'd have to look it up. It's got to be in the range of 9 to 13. Yep. All right, others?
So we can just consider that the same as like.
You can consider that basically the same as having an adjacent carbonyl. Yes?
So just checking with the enolate, if you were to treat it with LDF, would it still?
Yeah, if you were to treat this with LDA, would it still use that proton? Yes, because this proton is especially acidic. And the reason is the base is, the conjugate base is stabilized by resonance. Remember, the LDA steric base selectivity only kicks in when pKa's are similar. Otherwise, the differences in acidity will matter more. Okay, others? All right, let's do a thinking backwards one. So in a retrosynthetic sense, this comes straight out of your text. So this is problem 1826A. Here is a product, and they tell you what starting materials are needed to make this product by the Michael reaction. So you already know it's not as open-ended as you think. You already know what you're supposed to do. Now, I drew it that way because that is the way it is drawn in your text. Some of you are going to get tripped up by the CO2ET abbreviation. You may not be sure what to do with that. That is an abbreviation for an ester. So what that means is carbonyl here, oxygen here, ethyl group there. Okay. So with that, we need to recognize a Michael product. Remember the key principle. Michael products are 1,5 dicarbonyl compounds. So we're looking for a 1,5 relationship between carbonyls. So I'm just going to start counting on the left. 1, 2, 3, 4, 5. I could have counted this way to 5. I could have started with the ones on the right and counted backwards either way. Excuse me. The carbonyls are 5 atoms apart, or at positions 1 and 5 respectively. So now we got to decide which portion we think was the electrophile, and we'll remind ourselves that in a Michael reaction, the electrophile was an alpha-beta unsaturated carbonyl compound. And we need to decide which part of the molecule was the nucleophile, which we're reminding ourselves is an enolate in the Michael reaction. And we're going to have a couple of different choices that we can make. I'll start with one of them. So let's imagine that this portion was our carbonyl carbon of our electrophile. That would make this the alpha carbon and this the beta carbon. That would make this the bond that we made in the Michael reaction. And that would make this the purple alpha carbon of the enolate. If you break it apart in that direction, then your electrophile is this molecule, this alpha beta unsaturated carbonyl compound, and your nucleophile should be this portion, and we'll just draw the enolate. Though, of course, if we were going to draw our starting material, we would draw the conjugate acid of the enolate. Here's the purple alpha carbon. Here's the negative charge on it. All right. Does that make sense? Now, some of you are going to ask, what if you started on the other side? So, no, that's fine. I want all that there. What if instead you decided, well, what if one of those other carbonyls is the starting point for my electrophile? So let's go through and do that analysis and see what we would come up with. Supposing I wanted this to be the orange carbonyl carbon, that would make this alpha, this beta. That would say that I made this bond, and that would make this the alpha carbon of the enolate. If I divided it up that way, my electrophile would be something like this. And my nucleophile would be something like this. Do you see how I did that? Now, you're going to be wondering which of these answers is wrong, and if it is, how will I recognize it? And the short answer is the one on the bottom is not wrong, but the one on the top is the best option. And the reason it's the best option because you're using a very stable enolate, meaning that it's going to be very easy to deprotonate the conjugate acid. In contrast, the one below is sort of a less good option because the enolate is not as stable and more difficult, and the corresponding conjugate acid is more difficult to deprotonate. So the one on the bottom isn't wrong, but when you're doing problems in the text and you're faced with this situation, if you have a choice, the text will almost always choose the one where you can use the better enolate. Okay. Follow-up questions? Yeah.
This kind of goes back to the previous section, but when you attach the nucleophile, the enolate to the beta carbon, the cyclo molecule, isn't there? So when you get rid of the double bond between the alpha and beta, shouldn't there be like a lone pair on there making it negative?
Yes, you're right, and that's what we would do if we were drawing the mechanism. I was just showing you what the final product was. Yep, because remember in the mechanism, this isn't the exact same thing, but this is the intermediate you're referring to, and that gets protonated in the next step. And so the product no longer has a negative charge on the alpha carbon. Yep, yes?
Can that protonation be done with like aqueous workup, or does it
Can that protonation happen because of aqueous workup? Does it have to happen then? It turns out these reactions all occur in protic solvents, so you don't have to wait for any kind of workup. The protons are just there. What else? Yeah?
If you go down for the retrosynthesis, you said that the textbook is almost always going to use the top answers. Is that you're not using absolutes, or is there situations in which we would use the bottom?
So are there situations where you would use the bottom? I would prefer this one always. Sometimes there will be less clear of a choice. I'll just show you briefly another example from your text where maybe the choice is a little bit less clear. This is 18.26b, and for this one, depending on which carbon you count from, there's not really a clear choice. I'll try to illustrate that really quickly. If I call this the carbonyl carbon, this the alpha carbon, this the orange beta carbon, then that would be this bond that's formed, and then this one is my alpha carbon and my enolate. If I go that way, then my starting materials are this one and this enolate. Does that make sense? Alternatively, if I take the same starting material and I decide I want the other side to be the electrophile, that would make this one the beta carbon, and then this one the purple alpha carbon. This would be the bond that I made. And then if I thought backwards that way, what I'm actually proposing is an intramolecular Michael reaction. And you wouldn't necessarily know. There are things organic chemists know to learn whether this kind of intramolecular Michael reaction is going to be possible. I'm going to use color just to help out real quickly. Sorry, I'm backing up. In the top way of breaking the molecule apart, you've got this. In the bottom way, at least I've had students come to my office before and they tell me the answer says this, I did this. Is this wrong? And the answer is no, it's not wrong. And it's a perfectly reasonable thing to do. I certainly wouldn't have penalized you for it. I was going to say that the text has, or rather in organic chemistry, we have some data on what types of intramolecular reactions are favorable versus which aren't. And so it's possible the text is choosing this one because that's what the people who did the reaction did. It's not that this wouldn't work, it's just that this was synthetically easier. So on an exam question, I wouldn't have this be A and this be B, and you'd have to choose between the two. Likely only one of them would be there. Yeah. So this is your text answer because it's probably based on what people actually did. When people write textbooks, they try to find actual examples in chemistry papers of these reactions, not just making them up. This one seems reasonable, but there might be some issues with it that you wouldn't anticipate in an introductory OChem class and that I wouldn't expect you to worry about. This one up here would probably be synthetically easier. It would be easier to make these starting materials than this one. Okay. All right, so that's the Michael reaction. We need to move on next to a reaction called the Robinson annulation. Fortunately, this isn't its own thing. Annulation refers to making a ring. That's a word I think we've talked about before. This isn't really its own new reaction. In fact, it is two tandem reactions. The first is a Michael reaction, which we've just barely talked about. And then the second is an intramolecular aldol reaction, which we talked about 2 classes ago. So, in some ways, this is going to be a review of everything we've learned in the chapter. Now, the bad news is you're making a complicated ring, and some of the products are going to scare you. The good news is that if you practice it enough, it's not going to be as bad as you think. So, first step, the Michael reaction. This is just a review of what we barely talked about. In the Michael reaction, you have an electrophile, which is an alpha-beta unsaturated carbonyl compound, and then you have a nucleophile, which is going to be an enolate. So you'll be given starting materials, and you'll know what to do based on their structures. The alpha-beta unsaturated carbonyl compound is going to be the electrophile, and the other compound is going to be the enolate. In this example from your text, it's pretty clear which one should be the enolate because they're using a carbonyl compound that is especially acidic. So here's our purple alpha carbon. I'm awake. That was all we had time for. The alarm is wrong. I told you that my mom's ringtone on my phone, I always have my phone sort of silenced because I don't want it to go off during class, but my mom's ringtone is the Death Star alarm. Not because she's scary, but just because I should pay attention when my mom calls. I've told you this before too, but I love it so much I'll say it again. My father's ringtone is, I am your father. Yep. Okay, all right. So here is now the enolate. And here is the alpha-beta unsaturated carbonyl compound, which I'm going to draw like this. I want you to pay attention to this alpha-beta unsaturated carbonyl compound and notice that it's got another alpha proton. That one, the one that's pink, is going to be important later, but not now. I just want to highlight it because we will come back to it. In the Michael reaction, we expect the purple alpha proton to attack the beta carbon. Electrons move on to the alpha carbon to give us an enolate, which I'll draw here. We'll continue to label things. Here is the new bond we just made with the beta carbon. Oops. Oh, and got the eraser. Here's the new bond with the beta carbon, beta, alpha. And then here's the carbonyl carbon. And of course, that alpha carbon has a negative charge on it. And then the next step of the Michael reaction is we pick up a proton from our conjugate acid of our base, whatever that is. In this case, it's just water. And that will get us to the Michael product. And we'll look at it and you'll verify that it in fact is a 1,5-dicarbonyl compound. Where here's the alpha carbon of what was our enolate, here's the beta carbon of what was our electrophile. Over here's an alpha proton that we've highlighted before, but we're not worried about. Okay? And that is in fact a Michael product. You can tell because it's a 1, 2, 3, 4, 5 dicarbonyl, 1,5-dicarbonyl. All right. With me so far? Just another example of a Michael reaction. So in the second step, we're going to begin with an intramolecular aldol. This is something that you've seen before. Oops, I'm going to do that. You saw it before a couple of days ago, and you recall, and I'm going to erase some of the atoms here. You saw before that in an intramolecular aldol, where we have more than one alpha proton, we sort of have to worry about which alpha proton gets removed and which carbonyl gets attacked, okay? So I'm going to highlight 3 different kinds of alpha protons we have in this molecule. You have the pink alpha proton, you have the orange alpha proton, and then way over here you've got green alpha proton. Sorry, I guess I need to draw the protons. There we go. All right. And remember that in an intramolecular aldol reaction, we are not worried about making the more substituted enolate because in an aldol reaction, the products are in equilibrium with the starting materials. Therefore, enolate stability doesn't matter. What matters most is the stability of the products. So we want to choose the alpha proton to deprotonate that's going to give us the best aldol product, the most stable aldol product. It's pretty clear that we shouldn't do the orange one. If we made an enolate here and it attacked, say, the blue carbonyl, and actually this one and this one are identical, so it doesn't matter which. If we made the orange enolate and it attacked at the blue carbon, that would be a 1, 2, 3, 4-membered ring. So we probably got better options than that. Let's look at the pink one. 1, 2, 3, 4, 5, 6. That looks pretty good. So that's probably one that we should consider. And in the Robinson annulation, it is always this one. It is always the pink alpha proton that gets deprotonated and does the attacking. I've had students come to my office before in practice problems and say, okay, pal, what about the green alpha proton? And they notice, hey, if the green alpha proton attacked this carbonyl, that's 1, 2, 3, 4, 5, 6 atoms away. That's a 6-membered ring too. You have to build a model to see this, and so this is why this is sort of beyond the scope of the class. But the resulting product from there has some more angle strain, and you also struggle to make the dehydrated aldol product as a result because of the geometry of the molecule. That's difficult to illustrate. I could do it, but it would be a waste of time in class because most of you aren't worried about it, so I'm going to skip that. If you want to see it, you can come talk to me, but you can also just memorize that for the most part, in the Robinson annulation, it is always the pink alpha proton that gets deprotonated and does the attacking, okay? So with that in mind, we'll show in the next step the pink alpha proton being removed by our base, which is OH minus. And what's going to follow is just exactly what you would expect for an intramolecular aldol reaction. That is, we're going to get the enolate. Okay, there's the pink alpha proton, and we're going to attack the blue carbonyl carbon. And actually, you can see that it shouldn't matter whether we attack this one or this one. They're the same by symmetry. So we'll just pick one of them. We'll do what's expected in an aldol reaction, attack, the alpha carbon attacks the carbonyl carbon to get a tetrahedral intermediate. So what I'm going to do now is just draw the carbonyl carbon that got attacked. Here is the oxygen in the tetrahedral intermediate. This is the negatively charged oxygen of our carbonyl, what used to be the carbonyl carbon. That adjacent carbon, the carbon adjacent to that one, has a methyl group on it. And then here is the bond to the pink alpha carbon. And we've got 1, 2, 3, 4, 5, 6 atoms between the pink alpha carbon and the carbonyl carbon. So I'm going to draw a 6-membered ring here. 1, 2, 3, 4, 5, and 6. Okay, and then carbon 2 has a carbonyl on it. And then over here I'm missing a carbonyl oxygen. All right, that's the tetrahedral intermediate after the intramolecular aldol. What follows is just exactly what you expect for the aldol reaction, which is we'll protonate on the negatively charged oxygen of that tetrahedral intermediate. That will generate this structure. And what you will see here, you will recognize as an aldol product itself. It is a beta hydroxy carbonyl compound. Here's an alpha carbon, here's a beta carbon. This is, the beta hydroxy carbonyl compound that is an aldol product. In the Robinson annulation, we do not stop at the aldol product. Instead, we proceed with the subsequent dehydration. And that happens in 2 steps via what we call an E1CB mechanism. That is, we remove the proton on the pink alpha carbon to get an enolate intermediate. And then the negatively charged electrons on that pink, negative charge lone pair on the pink alpha carbon is going to kick down and kick off the beta OH group. Negatively charged carbon can easily kick off an OH minus group. And when that happens, what we're left with is our Robinson annulation product. Okay, that is a long mechanism, probably the longest you'll have this semester, yeah.
Looking at the final product, there's the two hexane or hexene rings. I'm not
Uh-huh.
sure putting it off. Were that methyl group not to be there to hide heat in its place, is there any preference for where the pi bond goes?
So the question is interesting. If this were a methyl group, if this were not a methyl group, if it were a proton, could you have done the elimination from this side and gotten a different product? Probably, and that's probably why they put the methyl group there in the first place. For our purposes, though, when we're doing the Robinson annulation, we will always do it this way, in the way you would expect for just the straightforward intramolecular aldol. It's not that what you're suggesting isn't possible. It's just, I think they know it's possible and have deliberately chosen the examples to avoid that. Yeah?
Can now we just, because we have can we just do another conjugate addition of the mic?
Right, it's a great question. You'll notice that the product itself of the Robinson annulation is, I'm going to highlight it here. This is the way you recognize a Robinson annulation product. It is a cyclohexenone. And that is itself an alpha-beta unsaturated carbonyl compound. And so you're wondering, is this also an electrophile? Could another enolate attack there? That sounds reasonable, but your text doesn't do it, and so we don't worry about it. What else? Yep.
So with that, there's like that methyl group sticking out from the bond.
Yep.
The two rings. Is there stereochemistry involved in it?
There is stereochemistry involved at this methyl group. That stereochemistry is set in the Michael addition step, where the planar enolate, or the enolate that's at least planar at this alpha carbon, can either attack the from above or below on the beta carbon. And so you get both options there. Yep. Okay, so you're going to need to practice that mechanism and make sure you can do it. Now, one of the key things that you're going to be expected to do as a result is first, predict what products form from the Robinson annulation. Second, think backwards to what the starting materials were for a Robinson annulation. Because thinking backwards is harder, and because you've already seen this example of the mechanism in the forward direction, I'm not going to do predict products today. You've got to do that on your own. I want to spend our time on the thinking backwards, but you've got to be able to do both. Because it is exceedingly easy to write exam questions where you have to think backwards and say, what are the starting materials for this Robinson annulation? I think I just gave 9 points away or something like that on an exam. So pay attention to that. Here is an example from your book for thinking backwards through the Robinson annulation. Before we do that, let's look at our product from the Robinson annulation. Let's notice that the alpha and the beta carbons in the cyclohexene product, these are the two bonds that were made in that last intramolecular aldol reaction. Okay? Those are the bonds we made in the intramolecular aldol reaction. On the other side, you want to identify the orange alpha carbon and the orange beta carbon, and then this will be the bond that we made in the Michael reaction. If you can do that, it is easy to break the Robinson annulation product up into two parts. What's highlighted here is the alpha beta unsaturated carbonyl compound starting material. What's over here was the enolate. Let's do that in a slightly more horrific example. And this is going to take some practice, so please give yourself time to do this. Do not wait until the day before the exam, because by that point you will be too frantic to think through it clearly. And you've got to think through this calmly and clearly to be successful. All right, so here is a Robinson annulation product. I'm noticing, to begin with, the cyclohexenone ring. I'm noticing that there's a bunch of other stuff that is not a cyclohexenone ring. That is going to give me permission to ignore the stuff that's not the cyclohexene ring because it's not directly involved in the reaction. I'm going to continue to draw it, but I'm not going to think about it. And I'm not going to worry about it. All right? So the first thing we do when we find the cyclohexene ring is we identify the pi bond, the alpha-beta unsaturated carbon-carbon pi bond. That's pink alpha and pink beta, and those were the two bonds that we made during the intramolecular aldol. The second thing we're going to do is count from the carbonyl carbon here to the alpha carbon to the beta carbon, and that is the bond that we made in the Michael reaction. That means that these carbons that I'm highlighting in orange used to be the alpha-beta unsaturated carbonyl electrophile, and that these carbons, everything else, was the enolate.
Wait. Don't you, isn't the bond between the alpha and the beta carbons?
No, the bond that you make in the Michael reaction is always between the beta carbon and whatever's on the other side. And in the way we'd been thinking about things, this carbon here will be the alpha carbon of the enolate. So to think backwards, what you do is you first draw the electrophile, and it's helpful to draw it in the same orientation. This is the alpha carbon, this is the beta carbon. You now need a pi bond between alpha and beta carbons. This pink alpha carbon is the one that does the attack in the intramolecular aldol. Then on the other side, we're going to draw the rest of the molecule. Okay, on the purple alpha carbon, we have a methyl group. This is the one that's going to get deprotonated in the, to prepare for the Michael reaction. On what I've labeled here as the pink beta carbon, remember that that carbon made a bond with the pink alpha carbon in an aldol reaction. In order for that to have happened, there must have been a carbonyl oxygen there. Okay? And then that becomes our electrophile. That becomes what we use to make our enolate nucleophile. All right, so that's worth some fairly intense practice. Go ahead.
Wouldn't that be a less good enolate?
So if you're looking at this alpha carbon, why you're noticing that perhaps there's another one here. Why does this one get removed instead of this one? The answer is, if we draw what that enolate looks like, you can see that the lone pairs there are not only adjacent to a carbon-oxygen pi bond, but they're also adjacent to a benzene ring. So they're stabilized by resonance with the benzene ring too. That actually makes that the better enolate. Okay, well, happy Valentine's Day to you. Now remember, no class Monday, but Tuesday is Pretend Monday. So I'll see you back here Tuesday. Yep, see ya.